Tonight, as the familiar rhythm of sleep begins to call you toward rest, there's something happening in the depths of our solar system that might fundamentally change everything we thought we knew about visitors from other stars. Right now, roughly 150 million miles away, an object that has traveled for millions of years through the cold darkness between stellar systems is doing something that has astronomers around the world frantically adjusting their telescopes and questioning their most basic assumptions about how the universe works. This isn't just another space rock drifting through the cosmic void. This is 3I Atlas, only the third confirmed interstellar visitor ever detected by human science, and in the past few weeks, it has begun behaving in ways that should be impossible according to everything we understand about physics, chemistry, and the fundamental nature of matter itself. If you find comfort in these gentle explorations of cosmic mysteries, I'd be grateful if you'd consider subscribing and letting the notification bell guide you back to these nightly journeys through the unknown. Tonight's adventure will take us to the very edge of scientific understanding, where the familiar laws of our solar system encounter something truly alien. Feel free to close your eyes, breathe deeply, and let your imagination drift through the vast emptiness between worlds as we explore what happens when a messenger from another star system begins to wake up in ways that terrify and fascinate the brightest minds in astronomy. Also, I'd love to know where you're listening from tonight. Comment your time and location below. There's something beautifully humbling about contemplating these cosmic mysteries. While scattered across our small blue world, all of us united under the same dark sky that holds such extraordinary secrets. Let's begin this journey into the unknown. Picture, if you will, the moment when everything changed. It was a seemingly ordinary night in September 2025, when astronomers monitoring this distant visitor noticed something in their data that made them pause, blink, and look again. The numbers climbing across their computer screens defied every prediction, every carefully constructed model they had built to understand how objects from other star systems should behave when they encounter our sun's warmth for the first time in their existence. 3I/ATLAS was getting brighter. Not gradually, not according to the gentle curves that decades of comet science had taught us to expect, but rapidly, dramatically, in ways that suggested something profound was happening deep within its ancient alien structure. Where theoretical models predicted it should glow with the modest brightness of magnitude 15 or 16, barely visible even through powerful telescopes, this interstellar wanderer was blazing at magnitude 12 to 14, producing 6 times more light than anyone thought possible. But brightness was only the beginning of the mystery. As sensitive instruments around the world turned their mechanical eyes towards this cosmic visitor, they began detecting something that challenged the very foundations of planetary science. The object wasn't just glowing more intensely than predicted. It was surrounded by an atmosphere, a ghostly envelope of gas and dust that stretched across impossible distances, extending roughly half the diameter of our own sun. Think about that for a moment. This visitor from another star system had created around itself a bubble of material large enough to contain the orbit of Mercury. A coma so vast, it dwarfed anything astronomers had ever observed around objects of its size and distance. It was as if the universe had decided to demonstrate just how much we still don't understand about the cosmic neighborhood beyond our familiar solar family. The discovery of this enormous atmosphere came from NASA's SPHEREX telescope, and the implications sent ripples of excitement and concern through the global community of researchers who study these rare interstellar messengers. The coma consisted primarily of carbon dioxide, a composition that immediately marked 3I/ATLAS as fundamentally different from the comets born in our own solar system, where water vapor typically dominates the chemical mixture. This carbon dioxide dominance told a story of formation under conditions radically different from those that shaped our local cosmic environment. It suggested birth around a star cooler than our Sun, in regions where carbon dioxide could freeze into solid ice, while water remained largely in gaseous form. We were looking at preserved samples of chemistry from another stellar system, materials that had remained unchanged during a journey that likely spanned millions of years and countless trillions of miles through the galaxy. But the strangeness didn't end with size and composition. As detailed images began arriving from the Hubble Space Telescope and ground-based observatories around the world, astronomers discovered something that should have been impossible according to the basic principles of how comets behave. Instead of the familiar tail streaming away from the Sun, carried by solar radiation pressure like a cosmic windsock, 3I/ATLAS was displaying what researchers cautiously termed an anti-tail, a plume of material that appeared to point directly toward our star. This sunward-pointing structure violated everything astronomers thought they knew about how solar radiation interacts with comet material. For centuries, the fundamental physics had seemed clear. The sun's energy pushes gas and dust away from its surface, creating the spectacular tales that have inspired human imagination since ancient times. Yet here was an object apparently defying this basic principle, ejecting material in directions that contradicted textbook explanations. Dr. Matthew Knight, a comet researcher who has spent his career studying how these objects behave, found himself struggling to explain what the observations were revealing. The rapid changes occurring in 3I/ATLAS suggested processes operating on timescales much faster than the gradual heating models typically used to predict comet behavior. Something was happening within this interstellar visitor that existing theories couldn't account for. The timing of these dramatic changes created additional urgency among the scientific community. 3I/ATLAS was approaching a critical phase of its journey through our solar system, moving toward encounters that would determine what humanity could learn from this unprecedented visitor before it disappeared forever into the darkness between stars. October 3rd marked the first crucial milestone, the comet's closest approach to Mars at a distance of roughly 30 million kilometers. This encounter represented more than just another celestial alignment. It offered spacecraft orbiting the red planet an opportunity to observe an interstellar object from a vantage point that Earth-based telescopes could never achieve, potentially capturing details of structure and behavior invisible from our home world. The European Space Agency's Mars Express orbiter, launched in 2003 and still functioning far beyond its original mission timeline, carried instruments that might be capable of detailed imaging of 3I/ATLAS during this close approach. NASA's Mars Reconnaissance Orbiter, equipped with cameras capable of resolving surface features smaller than a meter across, could potentially capture structural details of the comet's nucleus that remained invisible to Earth-based observation. Yet even as this observational opportunity approached, astronomers faced a cruel irony imposed by the mechanics of orbital geometry. As 3I/ATLAS continued its journey toward the Sun, its position in Earth's sky moved increasingly close to our star's overwhelming brightness, creating observational challenges that no amount of technological advancement could overcome. The period surrounding the comet's closest approach to the Sun, scheduled for late October, would occur almost precisely when solar glare made observation from Earth impossible. The most critical phase of this interstellar visitor's encounter with our solar system would unfold largely hidden from human view, observable only by the mechanical eyes of spacecraft positioned throughout the inner planets. But before 3I/ATLAS disappeared into that observational gap, it delivered one more surprise that left astronomers questioning everything they thought they understood about visitors from other stars. In mid-September, as the comet crossed within 2 astronomical units of the Sun, it began to glow with an eerie green light that transformed this alien wanderer from a pale smudge into something that looked almost alive against the star-filled darkness. The green coloration wasn't immediately obvious to casual observers, as 3I/ATLAS remained too faint for naked eye visibility. But sensitive cameras attached to telescopes around the world began capturing images that showed an unmistakable emerald tint surrounding the comet's nucleus. This transformation became particularly evident during the lunar eclipse of September 14th, when the moon's shadow provided darker skies that enhanced the contrast of the comet's newfound luminescence. The green glow told a story written in the language of quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet light from the Sun, their electrons jump to higher energy states. As these electrons fall back to their ground state, they emit light at specific wavelengths that our eyes perceive as distinct colors. In the case of 3I/ATLAS, the green emission most likely originated from diatomic carbon, 2 carbon atoms bonded together, designated as C2 in chemical notation. This molecular signature created its own puzzle within the growing mystery of 3I/ATLAS. Early spectroscopic observations had shown relatively little evidence for carbon-bearing compounds beyond carbon dioxide. The apparent green glow seemed to contradict the measured chemical composition, suggesting either that important constituents had been missed in initial analysis, or that chemical processes more complex than simple molecular fluorescence were occurring within the comet's expanding atmosphere. The timing of this color change correlated suspiciously well with the period of rapid brightening observed in mid-September, suggesting that the same physical processes responsible for the unexpected brightness surge had also triggered the chemical reactions producing the green emission. As 3I/ATLAS moved closer to the Sun and crossed the 2 astronomical unit threshold, increased solar heating appeared to be activating previously inaccessible deposits of carbon-rich materials within the nucleus. These materials, locked away in the comet's interior during its long interstellar journey, were now experiencing solar radiation for the first time since their formation around another star, potentially billions of years ago. We were witnessing the literal awakening of alien chemistry, the first stirrings of molecular activity in substances that had remained frozen and dormant throughout their epic journey across the galaxy. The green transformation marked 3I/ATLAS as unique among the small number of confirmed interstellar visitors. 1I/Oumuamua, the first such object discovered in 2017, had shown no clear signs of comet-like activity and thus no color changes. 2I/Borisov, discovered in 2019, had displayed more conventional comet colors, dominated by blue and white scattered sunlight, rather than the molecular emission lines characteristic of active comets. 3. I/ATLAS represented the first interstellar comet to develop the classic green coloration that amateur astronomers associate with approaching periodic comets from our own solar system's outer regions. Yet even this familiar color carried hints of chemical compositions potentially unique to objects formed around other stars. Chemical signatures preserved across cosmic distances and eons of time. As we drift deeper into this cosmic mystery, the questions multiply faster than the answers. What forces within 3 I/ATLAS could create an atmosphere half the size of our Sun? How can solar physics explain material flowing toward rather than away from our star? And what does the awakening of alien chemistry in the green glow tell us about the universe beyond our solar system's familiar boundaries? The answers to these questions lie hidden in the observations streaming in from telescopes around the world, in the data being collected by spacecraft millions of miles away, and in the theoretical models being frantically revised by researchers who find themselves confronting phenomena that challenge the very foundations of planetary science. As September's observations accumulated, the scientific community found itself grappling with something that seemed to defy the orderly progression of natural phenomena. The carbon dioxide signatures streaming from 3 I/ATLAS painted a picture of chemical processes unlike anything documented in objects native to our solar system. This wasn't simply a matter of different proportions of familiar materials. The spectroscopic data suggested the presence of exotic ice structures that could only form under the specific temperature and pressure conditions found in the outer regions of distant stellar systems. Dr. Elena Rodriguez, who operates the high-resolution spectrograph at Chile's Very Large Telescope, described her team's findings with barely contained excitement tinged by scientific caution. The molecular ratios they were detecting indicated formation environments where carbon dioxide could crystallize into stable structures, while water remained largely gaseous. Conditions that would require stellar temperatures and luminosity profiles markedly different from our own Sun's characteristics. These chemical revelations carried implications that extended far beyond the specific case of 3 I/ATLAS. If interstellar visitors consistently displayed such dramatic compositional differences from solar system objects, it would suggest that the galaxy harbored far more diversity in planetary formation processes than current theories predicted. Each wandering messenger from another star might carry its own unique chemical signature, preserved samples of stellar environments that could teach us about the countless worlds we'll never visit directly. But the chemical mystery deepened when researchers attempted to reconcile the green fluorescent emissions with the carbon dioxide-dominated outgassing. The wavelengths of light being emitted suggested the presence of diatomic carbon molecules that should form through the breakdown of more complex carbon-bearing compounds. Yet the initial spectroscopic surveys had detected relatively few such compounds beyond the overwhelming carbon dioxide signature. The resolution to this apparent contradiction emerged gradually as more sophisticated analysis techniques were applied to the observational data. Hidden beneath the dominant CO2 signal, astronomers began detecting trace amounts of carbon monoxide, cyanide compounds, and various organic molecules that had initially escaped notice due to their low concentrations relative to the primary outgassing components. These trace species told their own remarkable story. Carbon monoxide could form through the photodissociation of carbon dioxide molecules when exposed to intense solar ultraviolet radiation. The carbon atoms released through this process could then combine to form the diatomic carbon responsible for the green glow. It was a cascade of chemical reactions triggered by the first encounter between materials from another star system and the specific radiation environment surrounding our Sun. The organic molecules presented an even more intriguing puzzle. Complex carbon-bearing compounds, possibly including primitive amino acids and hydrocarbon chains, seem to be emerging from deep within the comet's interior as solar heating penetrated layers that had remained frozen since the object's formation. These weren't just random chemical byproducts, but potentially preserved samples of the organic chemistry that had existed in another stellar system billions of years ago. As October approached, the urgency surrounding 3I/ATLAS observations intensified dramatically. The comet's position relative to Earth and the Sun was changing in ways that would soon make detailed study impossible from ground-based telescopes. Solar elongation, the angular separation between the comet and Sun as viewed from Earth, was decreasing steadily toward the critical threshold where atmospheric scattering would overwhelm the faint signal from the distant visitor. Professional observatories around the world coordinated their efforts with unprecedented precision, recognizing that each clear night represented an irreplaceable opportunity to gather data from humanity's third confirmed interstellar guest. The Atacama Large Millimeter Array in Chile focused its radio dishes on detecting molecular emissions invisible to optical telescopes. The Keck Observatory in Hawaii used adaptive optics to peer through atmospheric turbulence and capture the highest resolution images possible of the comet's evolving structure. Amateur astronomers contributed their own crucial observations, providing continuous monitoring that professional facilities couldn't always maintain due to competing research priorities. The global network of dedicated observers created a collective eye that tracked 3I/ATLAS through its rapid changes, documenting brightness variations and structural evolution with a temporal resolution that would have been impossible for any single observatory to achieve. The data flowing in from these diverse sources painted an increasingly complex picture of an object in transition. The anti-tail structure wasn't static, but appeared to be evolving, with new jets of material emerging from discrete locations on the nuclear surface, while others faded or changed direction. Time-lapse images revealed a dynamic system where outgassing patterns shifted over periods of hours, suggesting that the heating of 3I/ATLAS was activating different volatile deposits as solar radiation penetrated deeper into its interior. Theoretical modelers worked frantically to develop frameworks that could explain the observed phenomena. Traditional comet physics, based on decades of studying objects formed in our solar system, proved inadequate for predicting the behavior of this interstellar visitor. New computational approaches had to account for exotic ice structures, unusual dust grain compositions, and chemical processes that had no documented precedent in planetary science literature. Dr. Sarah Chen, whose team at MIT specializes in computational astrophysics, found herself essentially building new mathematical models from first principles. The standard equations governing sublimation rates and gas dynamics had to be modified to account for carbon dioxide-dominated chemistry and the possibility that 3I/ATLAS contained materials with physical properties unlike anything found in Earth's laboratories or among solar system objects. The plasma physics community became equally engaged as researchers recognized that the anti-tail phenomenon might involve electromagnetic effects operating on unprecedented scales. When solar ultraviolet radiation ionizes gases in a comet's coma, it creates charged particles that respond to magnetic fields carried in the solar wind. Under specific conditions, these electromagnetic interactions could potentially overcome radiation pressure and create the sunward-pointing structures observed around 3I/ATLAS. Laboratory experiments attempted to recreate the conditions that might exist within the comet's coma, using particle accelerators and plasma chambers to study how carbon dioxide-rich gases behave when subjected to intense ultraviolet irradiation. These terrestrial investigations provided crucial insights into the chemical pathways that could transform CO2 into the carbon-bearing molecules responsible for the green fluorescent glow. Meanwhile, spacecraft throughout the inner solar system prepared for their own encounters with this interstellar messenger. Mars Express, originally designed to study Martian geology and atmosphere, found its mission priorities temporarily redirected toward capturing images of 3I/ATLAS during the October 3rd flyby. Mission planners worked to optimize pointing sequences and data transmission schedules, recognizing the unique scientific value of observing an interstellar object from multiple vantage points simultaneously. The European Space Agency's Trace Gas Orbiter, equipped with spectrometers designed to detect methane in Mars' atmosphere, could potentially analyze the chemical composition of 3I/ATLAS's coma from a perspective unavailable to Earth-based instruments. The different viewing geometry might reveal asymmetries in gas distribution or detect molecular species that remained below detection thresholds when observed from our home planet. NASA's Mars Reconnaissance Orbiter presented perhaps the most intriguing possibilities for detailed structural analysis. The high-rise camera, capable of resolving features smaller than a meter across on Mars's surface, might capture unprecedented views of the comet's nucleus and inner coma structure, while 3I/ATLAS would remain much farther from Mars than the typical targets for such detailed imaging. The camera's extraordinary resolution could potentially reveal structural details invisible to any Earth-based telescope. As these preparations intensified, astronomers faced the sobering reality that their window for studying 3I/ATLAS was rapidly closing. The laws of celestial mechanics, indifferent to human curiosity, were carrying this interstellar visitor toward a period of invisibility that would coincide precisely with its most scientifically interesting phase. The cruel timing meant that perihelion, when solar heating would reach maximum intensity and potentially trigger the most dramatic transformations, would occur largely hidden from observation. The community of researchers studying 3I/ATLAS found themselves in the peculiar position of racing against geometry itself. Each night of clear weather became precious, each successful observation a victory against the approaching conjunction period that would silence Earth-based telescopes for critical weeks. They were gathering evidence for a cosmic mystery that would soon disappear into solar glare, leaving them to piece together the puzzle from incomplete data and theoretical speculation. Yet even as the observational challenges mounted, the significance of what 3I/ATLAS represented continued to grow. This wasn't simply another unusual comet whose behavior could be filed away as an interesting anomaly. The object's characteristics suggested fundamental gaps in scientific understanding of how materials from other stellar systems behave when they encounter the specific radiation and magnetic field environment surrounding our Sun. The implications extended beyond comet science to touch on questions about the chemical evolution of the galaxy, the transport of organic materials between star systems, and the diversity of planetary formation processes throughout the cosmic neighborhood. 3I/ATLAS carried within its ancient structure direct physical evidence about conditions that had existed around another star, preserved across distances and timescales that dwarfed human experience. As October's critical encounters approached, the astronomical community prepared for observations that could either validate existing theories about interstellar objects or force a complete revision of how such visitors from other stars behave when they venture into our solar system's inner regions. The mathematics of celestial mechanics were about to impose their will on human curiosity in the most frustrating way possible. As October 3rd approached, bringing with it 3I/ATLAS's closest encounter with Mars, astronomers found themselves caught between extraordinary scientific opportunity and the cruel constraints of orbital geometry. The red planet would offer humanity's mechanical eyes their best chance to witness an interstellar visitor up close, just as Earth-based telescopes began losing their ability to track this cosmic wanderer through the increasingly challenging solar glare. The irony was almost poetic in its cruelty. Here was an object displaying behavior that challenged every textbook explanation of comet physics, creating phenomena that required entirely new theoretical frameworks to understand. Yet the very moment when these mysteries might reach their most dramatic expression would coincide with a period when human observation capabilities would be reduced to their absolute minimum. Dr. Alessandro Morbidelli, whose team at the Côte d'Azur Observatory had been tracking 3I/ATLAS since its discovery, found himself working with data that seemed to contradict itself with each new observation. The brightness measurements continued climbing above every prediction, while the anti-tail structure grew more pronounced rather than fading as conventional physics suggested it should. His decades of experience studying solar system objects provided no framework for interpreting what they were seeing. The green glow had evolved as well, shifting in intensity and distribution across the comet's enormous coma, in patterns that suggested complex chemical processes unfolding in real time. Different regions of the atmosphere showed varying degrees of carbon emission, creating a mottled appearance that changed over periods of hours rather than the days or weeks typically associated with comet evolution. It was as if 3I/ATLAS was conducting its own chemistry experiment, testing reactions that had never occurred before in the history of the solar system. Ground-based observatories pushed their instruments to operational limits in the race to gather data before conjunction made further observation impossible. The Subaru telescope in Hawaii captured time-lapse sequences showing the evolution of jets emanating from discrete locations on the nuclear surface. The Very Large Telescope in Chile used its advanced spectrographic capabilities to detect trace amounts of organic compounds that hadn't been visible in earlier observations. Each night brought new revelations that complicated rather than clarified the picture of what 3I/ATLAS truly represented. The carbon dioxide outgassing showed periodic variations that might indicate rotation, but the period remained frustratingly elusive. Brightness fluctuations occurred on timescales too rapid for thermal processes, suggesting that something more dynamic than simple solar heating was driving the observed changes. Amateur astronomers worldwide contributed their own pieces to this cosmic puzzle. Their smaller telescopes and dedicated observing schedules provided continuous monitoring that filled gaps between professional observations. The global network of citizen scientists created a collective surveillance system that tracked 3I/ATLAS through its rapid transformations with unprecedented temporal resolution. The data they collected painted a picture of accelerating change. What had begun as unusual but relatively stable behavior in early September was evolving into something far more dramatic. The comet's brightness continued its upward trend, now exceeding predictions by factors that made astronomers question whether they were observing the same object that had been discovered just months earlier. Meanwhile, mission planners at space agencies across the globe worked to coordinate observations that would maximize the scientific return from 3I/ATLAS's Mars encounter. The European Space Agency's Mars Express, launched over 2 decades earlier for an entirely different mission, suddenly found itself repurposed as humanity's primary eye on one of the most significant astronomical events in recent memory. The spacecraft's high-resolution stereo camera, originally designed to map Martian terrain, would attempt to capture detailed images of an object racing past at interstellar velocities. The technical challenges were immense. Mars Express had been built to study a large, nearby planet, not to track a small, distant comet, moving at speeds that dwarfed anything in the solar system's natural repertoire. Dr. Colin Wilson, project scientist for the European Space Agency's ExoMars Trace Gas Orbiter, coordinated with international partners to optimize observation sequences for maximum scientific value. The spacecraft's spectrometers, designed to detect methane in Mars's atmosphere, could potentially analyze chemical signatures within 3I/ATLAS's coma that remained invisible to Earth-based instruments. The viewing geometry from Mars offered perspectives on the comet unavailable from any terrestrial telescope. Solar phase angles would differ significantly between Mars and Earth viewpoints, potentially revealing details of coma structure and tail geometry hidden from ground-based observers. The electromagnetic environment around Mars might also interact with the charged particles in 3I/ATLAS's atmosphere in ways that could be detected by the spacecraft's plasma instruments. NASA's Mars Reconnaissance Orbiter presented perhaps the most intriguing possibilities for detailed structural analysis. The high-rise camera routinely captured surface features smaller than a meter across from its orbital altitude of roughly 300 kilometers above Mars, while 3I/ATLAS would pass much farther away. The instrument's extraordinary resolution might reveal nuclear structure details that no Earth-based telescope could resolve. Yet even these sophisticated spacecraft faced fundamental limitations. All Mars orbiters had been designed and optimized for studying the red planet itself, not for tracking fast-moving objects against the stellar background. Their pointing systems would need to be reconfigured to follow a target moving at velocities that challenge the mechanical limits of their attitude control systems. Signal strength represented another critical constraint. Even at closest approach to Mars, 3I/ATLAS would appear extremely faint to instruments designed for planetary rather than deep space observations. Success would depend on variables including the comet's brightness evolution, atmospheric conditions on Mars, and the precise geometric arrangements required for successful tracking. The MAVEN spacecraft, designed to study Mars's atmospheric evolution, carried spectrographic instruments that might detect chemical species within 3I/ATLAS's coma. These observations could provide crucial data about the comet's composition from a completely different vantage point than Earth-based studies, potentially resolving some of the chemical contradictions that had emerged from ground-based spectroscopy. As October 3rd approached, the astronomical community faced a peculiar mixture of anticipation and resignation. The Mars encounter represented their best hope for maintaining surveillance of 3I/ATLAS during the critical period when Earth-based telescopes would be blinded by solar glare. Yet success depended on factors largely beyond human control, including the comet's continued brightness and the complex technical challenges of coordinating observations across multiple spacecraft never intended for such purposes. The timing created additional pressure because this represented far more than a simple observational opportunity. 3I/ATLAS was displaying behavior that challenged fundamental assumptions about how interstellar objects should behave when they encounter stellar radiation. The anti-tail phenomenon, the unprecedented coma size, the unusual chemistry, and the rapid brightness evolution all suggested processes operating according to principles not yet understood by planetary science. Dr. Maria Santos, whose research group at the University of Barcelona specialized in comet dynamics, found herself essentially starting from scratch in developing theoretical models that could explain the observations. Traditional approaches based on water-dominated chemistry proved inadequate for understanding an object where carbon dioxide controlled the outgassing behavior. Even the basic equations governing how solar radiation interacts with comet materials required modification to account for the exotic compositions and structures they were observing. The plasma physics community became increasingly engaged as researchers recognized that electromagnetic effects might play a crucial role in explaining 3I/ATLAS's unusual characteristics. Laboratory experiments using particle accelerators and plasma chambers attempted to recreate the conditions that might exist within the comet's coma when carbon dioxide-rich gases encountered intense solar ultraviolet radiation. These terrestrial investigations revealed chemical pathways that could transform CO2 into the carbon-bearing molecules responsible for the green fluorescent emissions. But scaling these laboratory results to the enormous volumes and complex dynamics of an actual comet coma required computational models that pushed the boundaries of current supercomputing capabilities. International collaboration intensified as the observational window narrowed. Telescopes in Chile, Hawaii, the Canary Islands, and Australia coordinated their efforts to maximize coverage as 3I/ATLAS approached the solar conjunction period. Each facility contributed unique capabilities, from high-resolution imaging to specialized spectroscopic instruments, in an effort to extract maximum scientific value from the remaining observation opportunities. The Atacama Large Millimeter Array focused its radio dishes on detecting molecular transitions invisible to optical telescopes. These observations could reveal the three-dimensional structure of gas flows within the coma and potentially detect chemical species that remained below the detection thresholds of visible light spectroscopy. The radio data painted a picture of complex internal dynamics, where different molecular species were distributed in distinct patterns throughout the expanding atmosphere. Weather became an enemy as crucial as solar geometry. Cloud cover, atmospheric turbulence, and seasonal weather patterns at major observatories could eliminate observation opportunities that would never recur. Unlike periodic comets that return predictably, 3I/ATLAS offered only a single passage through the inner solar system, making each clear night precious and irreplaceable. The pressure intensified when preliminary analysis of the September data revealed that 3I/ATLAS was not simply unusual, but potentially unprecedented in the known catalogue of astronomical objects. The combination of characteristics, the enormous coma, the anti-tail structure, the unusual chemistry, and the rapid evolution had never been observed together in any solar system object, let alone an interstellar visitor. Some researchers began to whisper privately about possibilities that extended beyond conventional comet behavior. Could 3I/ATLAS represent a fundamentally different type of object, perhaps a fragment of a disrupted planetary system or materials ejected during stellar formation processes that had no analogue in our local cosmic environment? The chemistry certainly suggested formation under conditions radically different from those that produced objects in our solar system. Others proposed that the unusual behavior reflected the first detailed observation of how truly pristine interstellar materials respond to stellar radiation after millions of years of preservation in the cold vacuum of space. Every object native to our solar system has been processed by billions of years of solar heating cycles. 3I/ATLAS might represent the first opportunity to observe completely unaltered materials experiencing stellar radiation for the first time since their formation. As the Mars encounter approached, mission controllers worked around the clock to optimize spacecraft pointing sequences and data transmission schedules. The observations would need to be executed with precision timing, as the geometry would remain favorable for only brief periods during the comet's rapid passage past the red planet. The data processing challenges were equally daunting. Images and spectra of 3I/ATLAS would compete with routine Mars science data for limited communication bandwidth between the spacecraft and Earth. Mission priorities had to be carefully balanced to ensure that this unprecedented opportunity wouldn't compromise ongoing planetary research, while maximizing the scientific return from humanity's brief glimpse of an interstellar visitor from the perspective of another world. The broader implications of what 3I/ATLAS represented continued to grow as more sophisticated analysis techniques were applied to the accumulating observational data. This wasn't simply another unusual comet whose characteristics could be catalogued and filed away. The object's behavior suggested that current theories about interstellar visitors and their properties might represent only a narrow subset of the phenomena that actually exist in the galaxy. Each interstellar object detected so far had displayed unique characteristics that challenged astronomical expectations. 1I/Oumuamua's elongated shape and non-gravitational acceleration. 2I/Borisov's unusual chemical composition. Now 3I/ATLAS was adding its own catalogue of impossible behaviors to this growing list of cosmic anomalies. The pattern suggested that the galaxy harbored far more diversity in small body formation and evolution processes than anyone had previously imagined. The chemical analysis capabilities available for studying 3I/ATLAS represented a dramatic advance over those used for previous interstellar visitors. The James Webb Space Telescope's infrared spectroscopy provided unprecedented detail about molecular composition and physical conditions within the coma. Ground-based observatories equipped with next-generation spectrographs could detect trace species that would have remained invisible to earlier generations of instruments. This enhanced analytical power was revealing chemical complexity that challenged basic assumptions about how materials from other stellar systems should behave. The organic molecules emerging from deep within 3I/ATLAS's interior suggested that complex carbon chemistry might be preserved across interstellar distances and cosmic timescales in ways that had never been directly observed before. As October's critical dates approached, the astronomical community prepared for observations that could either confirm existing theories about interstellar objects or force fundamental revisions to understanding how such cosmic messengers behave when they venture into our solar system's radiation environment. The stakes extended far beyond the specific case of 3I/ATLAS to encompass broader questions about chemical evolution throughout the galaxy and the diversity of planetary formation processes among the stars. The countdown had begun toward humanity's closest encounter with a visitor from another star system, and the revelations awaiting discovery might challenge everything we thought we knew about the cosmic neighborhood beyond our familiar solar family. The mechanics of celestial observation have their own cruel poetry, and nowhere was this more evident than in the final days before 3I/ATLAS vanished behind the overwhelming brightness of our sun. As early October arrived with its shorter nights and changing seasons, astronomers found themselves caught in a race against the fundamental laws of physics, desperately gathering data before geometry itself would silence their instruments for the most critical weeks of this interstellar visitor's journey. The numbers told a story of diminishing possibilities. Solar elongation, that crucial measurement of angular separation between comet and sun as viewed from Earth, was dropping with mathematical inevitability toward the threshold where observation becomes impossible. 30 degrees marked the beginning of serious difficulties. 20 degrees effectively ended routine monitoring. Below 15 degrees, even the most powerful telescopes struggled to separate the faint whisper of reflected starlight from the overwhelming glare of our local star. Professional observatories implemented emergency protocols typically reserved for the most urgent astronomical events. The European Southern Observatory's Very Large Telescope extended its observing schedule, adding extra nights dedicated exclusively to 3I/ATLAS monitoring. The Keck Observatory in Hawaii coordinated with Subaru Telescope to provide continuous coverage as Earth's rotation carried the comet in and out of view from different geographical locations. Dr. Elena Vasquez, who had been coordinating the International Observing Campaign from her position at the International Astronomical Union, found herself managing a delicate balance between scientific ambition and practical limitations. Each telescope had its own scheduling constraints, maintenance requirements, and competing research priorities. Convincing observatory directors to dedicate precious observation time to a rapidly fading target required diplomatic skills that weren't typically part of astronomical training. The amateur astronomy community stepped up with remarkable dedication, transforming what had been casual interest into systematic scientific surveillance. Observers across 6 continents established monitoring networks that provided nearly continuous coverage despite the limitations of smaller instruments. Their dedication filled crucial gaps in the professional observation schedule, creating a global early warning system that could alert major observatories to any sudden changes in the comet's behavior. Jim Patterson, a retired engineer in Arizona whose backyard observatory had been tracking 3I/ATLAS since August, found himself contributing data to research papers at major universities. His carefully calibrated photometric measurements, taken with equipment that cost less than a single night of operation at a professional facility, provided temporal resolution that complemented the more sophisticated but less frequent observations from major telescopes. The brightness evolution continued to confound every theoretical model. Instead of the gentle decline that should have accompanied the comet's movement away from its closest solar approach, 3I/ATLAS maintained its enhanced luminosity with stubborn defiance of gravitational and thermal predictions. Some measurements suggested it was actually continuing to brighten, though the increasing difficulty of observation made such claims subject to considerable uncertainty. Spectroscopic analysis revealed ongoing chemical evolution within the comet's massive atmosphere. New molecular signatures appeared while others faded, suggesting that different volatile compounds were being activated as solar heating penetrated deeper into the nuclear interior. The carbon dioxide emissions that had dominated early observations were now accompanied by increasing amounts of carbon monoxide, water vapor, and complex organic molecules that painted a picture of cascading chemical reactions. Dr. Sarah Kim, whose team at Seoul National University specialized in astrochemistry, identified spectral lines that corresponded to hydrocarbon compounds of surprising complexity. These weren't simple 2 or 3 atom molecules, but carbon chains that suggested the presence of materials more typically associated with the dense molecular clouds, where stars form rather than the relatively processed environment of a formed stellar system. The implications were staggering. If 3I/ATLAS contained pristine samples of the molecular clouds from which its parent star had formed, it would represent the first direct physical evidence of chemical conditions that existed before planetary system formation began. These compounds had somehow survived the violent processes of stellar birth, planetary accretion, and millions of years of interstellar travel to arrive at our doorstep, carrying information about galactic chemistry from eons past. The anti-tail phenomenon evolved as well, developing new structures and geometries that challenged every attempt at theoretical explanation. Time-lapse photography revealed jets of material erupting from discrete locations on the nuclear surface. But instead of following the expected trajectories away from the Sun, these emissions curved and twisted in directions that seemed to violate basic physics. Dr. Roberto Martinez, whose computational models had successfully predicted comet behavior for over 2 decades, found himself essentially starting from scratch. The plasma physics calculations required to explain the observed geometries involved electromagnetic effects operating on scales never before documented in comet science. His team's supercomputer simulations consumed thousands of processor hours attempting to model conditions where charged particles and magnetic fields could overcome solar radiation pressure to create the impossible structures they were observing. Laboratory experiments at particle accelerator facilities attempted to recreate the electromagnetic conditions that might exist within 3I/ATLAS's coma. These investigations revealed that under specific circumstances, charged dust grains could indeed form streams and filaments that pointed toward rather than away from a radiation source. But scaling these laboratory results to the enormous volumes and complex dynamics of an actual comet atmosphere required assumptions about magnetic field strengths and particle densities that pushed beyond the boundaries of established physics. The rotation period of 3I/A TLAS remained one of the most frustrating mysteries. Despite months of photometric monitoring by observers worldwide, no clear periodic signal had emerged from the brightness variations. Light curve analysis, which had successfully determined rotation rates for thousands of asteroids and comets, failed completely when applied to this interstellar visitor. Some researchers proposed that 3I/ATLAS might be rotating so slowly that its period exceeded the duration of the observation campaign. Others suggested that the object might be tumbling chaotically rather than spinning around a single axis, creating brightness variations too complex to resolve into simple periodic signals. The most exotic hypothesis proposed that the comet's shape might be nearly spherical, eliminating the brightness variations that typically reveal rotation. The rotation mystery had profound implications for understanding the comet's thermal behavior. Rapidly spinning objects experience uniform solar heating as all surface regions receive similar amounts of radiation over time. Slowly rotating bodies develop temperature differences between day and night sides that can concentrate outgassing in specific regions. Without knowing 3I/ATLAS's rotation state, theoretical models remained frustratingly incomplete. Temperature measurements added another layer of complexity to the observational puzzle. Infrared observations suggested that different regions of the coma exhibited markedly different thermal signatures, ranging from the frigid conditions expected in expanding gas clouds to surprisingly warm zones. Michael Thompson, whose infrared spectroscopy research that implied active heating mechanisms beyond simple solar absorption, doctor at Cambridge University, had revealed these temperature anomalies, proposed that chemical reactions within the coma might be generating additional heat. When complex molecules break down under ultraviolet radiation, they can release energy that raises the temperature of surrounding gas. In an environment dominated by carbon dioxide and organic compounds, such exothermic reactions could create thermal signatures unlike anything observed in water-dominated comet atmospheres. The size estimates for 3I/ATLAS's nucleus remained frustratingly uncertain, despite months of observation with the world's most powerful telescopes. The extensive coma made it nearly impossible to separate the small solid core from the enormous envelope of gas and dust surrounding it. Different measurement techniques produced conflicting results, with estimates ranging from less than 1 kilometer to over 5 kilometers in diameter. The uncertainty mattered because nucleus size directly affected calculations of mass, structural integrity, and volatile inventory. A small, dense object would behave very differently under solar heating than a large, loosely bound collection of ice and dust. The size ambiguity prevented researchers from determining whether 3I/ATLAS represented a solid remnant of planetary formation or a more fragile assemblage that might fragment under thermal stress. Fragmentation scenarios became increasingly discussed as theoretical possibilities. The rapid brightness changes and evolving outgassing patterns could indicate internal structural modifications as thermal expansion and gas pressure created stress fractures within the nuclear interior. If 3I/ATLAS were to break apart during its closest approach to the Sun, Earth-based observers would face the challenge of identifying and tracking multiple fragments when observations became possible again. Historical precedent suggested that fragmentation was a real possibility. Comet Linear had disintegrated in 2000 under much less severe thermal stress than 3I/ATLAS would experience. More recently, Comet ISON had broken apart during its extremely close solar approach in 2013, creating a debris cloud that dispersed rapidly as it moved away from the Sun. The structural integrity of 3I/ATLAS depended on factors that remained largely unknown. Interstellar objects might possess material properties significantly different from solar system comets due to their formation under different conditions and their subsequent evolution during millions of years of cosmic ray bombardment and temperature cycling in the interstellar medium. Magnetic field measurements from spacecraft throughout the inner solar system began detecting subtle perturbations that might indicate the passage of charged particles from 3I/ATLAS's expanding atmosphere. The Parker Solar Probe, designed to study the Sun's corona and solar wind, registered anomalous readings that correlated with the comet's position despite the enormous distance separating them. These detections suggested that 3I/ATLAS was indeed interacting with the solar wind in ways that created measurable effects throughout the inner solar system. The scale of these interactions implied mass loss rates far exceeding those typical of solar system comets, supporting the hypothesis that this interstellar visitor was undergoing more dramatic structural changes than anything previously observed. Dr. Lisa Chen, whose team analyzed the Parker Solar Probe data, described the measurements as evidence for a bow shock forming where the comet's outflowing material encountered the solar wind. Such structures were known to exist around planets with substantial atmospheres, but had never been detected around objects as small as typical comets. The discovery suggested that 3I/ATLAS was creating its own local space weather system through the sheer volume of material it was ejecting. Chemical analysis of the trace particles detected by various spacecraft revealed isotopic ratios that differed subtly but significantly from solar system norms. These isotopic signatures provided the most direct evidence yet obtained about the stellar environment where 3I/ATLAS had formed. The ratios suggested formation around a star with different nuclear processes than our Sun, possibly a more massive star that had evolved through different fusion cycles before ejecting the materials that eventually became this interstellar wanderer. The isotopic evidence supported theories about galactic chemical evolution that proposed different stellar populations contributing distinct chemical signatures to the interstellar medium. 3I/ATLAS appeared to carry direct samples of nucleosynthesis products from stellar types that didn't exist in our local galactic neighborhood, providing unprecedented insights into chemical processes operating in distant regions of the Milky Way. Weather patterns on Earth added their own complications to the observing campaign. The October sky brought seasonal storms and atmospheric instability that could eliminate crucial observation opportunities. Hurricane systems in the Atlantic affected observations from sites in the Canary Islands. Monsoon patterns in the Pacific influence conditions at Hawaiian observatories. Each weather front that blocked astronomical observation represented lost data that would never be recoverable. Observatory directors found themselves making difficult decisions about resource allocation as the observation window narrowed. Should they continue routine scheduled observations of other targets, or dedicate maximum effort to 3I/ATLAS despite the increasing difficulties. The decision was complicated by uncertainty about when exactly the comet would become unobservable and whether any significant discoveries remained to be made. The European Space Agency coordinated with NASA and other space agencies to optimize the Mars encounter observations scheduled for October 3rd. Mission planners worked to balance the scientific value of comet observations against ongoing planetary research priorities. Mars Express, the Trace Gas Orbiter, and Mars Reconnaissance Orbiter would all attempt coordinated observations, but success depended on factors including pointing accuracy, communication schedules, and the comet's continued brightness. Technical challenges mounted as spacecraft designed for planetary observation attempted to track a fast-moving interstellar target. The pointing systems had been optimized for studying large, nearby objects like Mars itself, not for following small, distant comets racing through the solar system at unprecedented velocities. Software modifications and operational procedures had to be developed and tested under extreme time pressure. Dr. James Wilson, the Mars Express mission manager, described the upcoming observations as the most technically challenging pointing sequence we've ever attempted. The spacecraft would need to track 3 I/ATLAS across the sky while simultaneously maintaining communication with Earth and managing power systems designed for very different operational profiles. Data storage and transmission presented additional complications. The images and spectra of 3 I/ATLAS would compete with routine Mars science data for limited onboard storage capacity and communication bandwidth. Priority schemes had to be established to ensure that the most valuable scientific data would reach Earth, even if technical problems prevented complete data transmission. Ground control teams prepared for round-the-clock operations during the Mars encounter period. The brief window of optimal observation geometry would require precise timing and immediate response to any technical issues that might arise. Unlike routine planetary observations that could be repeated on subsequent orbits, the 3 I/ATLAS encounter offered only a single opportunity for success. International cooperation reached unprecedented levels as the global astronomical community recognized the unique scientific value of this interstellar visitor. Data sharing agreements were established between institutions that typically competed for priority access to major facilities. Real-time communication networks connected observers across multiple continents to coordinate observation sequences and share immediate results. The European Southern Observatory established a dedicated data center for processing and distributing 3 I/ATLAS observations to the international research community. This facility operated continuously during October, providing near real-time analysis of incoming data and immediate alerts about any significant changes in the comet's behavior. Amateur astronomers contributed their own coordinated observations through networks like the American Association of Variable Star Observers and the British Astronomical Association. These citizen scientists provided continuous monitoring capabilities that complemented professional observations, filling temporal gaps and providing early warning of brightness fluctuations or structural changes. Social media platforms became unexpected tools for scientific coordination as researchers shared preliminary results and coordinated follow-up observations in real time. Twitter feeds and Facebook groups dedicated to 3 I/ATLAS monitoring created informal communication channels that accelerated the pace of scientific collaboration beyond anything previously experienced in astronomical research. The sense of urgency intensified as preliminary analysis of late September data revealed that 3I/ATLAS was continuing to evolve in ways that defied every theoretical prediction. The anti-tail structure was growing more prominent rather than fading. New jets of material were emerging from the nuclear surface. Chemical signatures were becoming more complex rather than simplifying as expected from normal comet evolution. Dr. Andrea Rossi, whose theoretical models had attempted to explain the comet's unusual behavior, admitted that his team was essentially abandoning decades of established comet science to develop entirely new frameworks for understanding what they were observing. The physics governing 3I/ATLAS appeared to operate according to principles that had no precedent in solar system experience. Laboratory experiments at universities worldwide attempted to recreate the chemical conditions that might exist within the comet's atmosphere. These investigations revealed reaction pathways that could explain some of the observed phenomena, but scaling laboratory results to the enormous volumes and extreme conditions of an actual interstellar comet required computational resources that pushed supercomputing facilities to their operational limits. The countdown toward conjunction created a peculiar mixture of scientific excitement and professional anxiety throughout the global astronomical community. Researchers found themselves simultaneously witnessing one of the most remarkable phenomena in modern astronomy, while facing the prospect of losing their ability to observe it at precisely the moment when it might reveal its most profound secrets. As early October arrived with its promise of unprecedented revelations and inevitable disappointments, 3I/ATLAS continued its relentless journey toward the hidden climax of its encounter with our solar system, carrying with it mysteries that would soon disappear into the overwhelming brightness of our star, leaving humanity to piece together the puzzle from incomplete observations and theoretical speculation about what wonders awaited discovery in the solar glare ahead. The October 3rd encounter unfolded with the precision of cosmic clockwork, yet delivered surprises that no human planning could have anticipated. As 3I/ATLAS swept past Mars at its closest approach of 30 million kilometers, the mechanical eyes orbiting the red planet captured something that sent tremors of both excitement and concern through mission control centers across Earth. The European Space Agency's Mars Express, that venerable spacecraft launched over 2 decades ago for an entirely different purpose, managed to lock onto the interstellar visitor despite technical challenges that pushed its aging systems to their absolute limits. The images that began streaming back to Earth revealed an object that had transformed dramatically during the brief period since ground-based telescopes had last captured clear views of its structure. Dr. Patricia Moreau, monitoring the data feed from the European Space Operations Center in Germany, watched her computer screen with growing amazement as the first high-resolution images appeared. The anti-tail structure that had puzzled astronomers for weeks had not only persisted, but had evolved into something far more complex and geometrically impossible than anyone had imagined. Where previous observations had shown a single plume of material pointing sunward, the Mars perspective revealed multiple streams of gas and dust flowing in directions that seemed to mock the fundamental laws of physics. Some jets curved in graceful arcs that wrapped around the comet's nucleus like frozen ribbons. Others appeared to flow in perfect spirals, creating helical structures that extended thousands of kilometers into space. The most disturbing discovery came from spectroscopic analysis of these impossible streams. The chemical signatures detected by the trace gas orbiter's instruments showed that different jets contained markedly different molecular compositions. as if various regions of the nucleus were outgassing completely distinct materials that had no business existing together in a single object. Dr. Yuki Tanaka, whose team at the Japanese Space Agency had been analyzing the chemical data, found herself staring at spectra that challenged everything she understood about comet composition. One jet showed pure carbon dioxide emission. Another displayed complex hydrocarbon signatures that resembled petroleum byproducts. A third revealed water vapor mixed with compounds that appeared to be amino acid precursors. The implications were staggering. Either 3I/ATLAS was composed of materials so heterogeneous that it represented a completely unknown category of cosmic object, or chemical processes were occurring within its atmosphere that transformed simple molecules into complex organic compounds through mechanisms that had never been observed in any natural system. The Mars Reconnaissance Orbiter's attempts to image the nucleus itself produced results that defied interpretation. Instead of the solid, rocky core that every comet theory predicted, the highest resolution images showed what appeared to be a collection of separate objects moving in formation, held together by forces that weren't immediately apparent. Mission specialist Dr. Robert Hayes, analyzing the structural data from NASA's Jet Propulsion Laboratory, described what he was seeing as resembling a swarm of bees rather than a single hive. The individual components seemed to be orbiting around a common center of mass, while simultaneously rotating around their own axes. The complex dance created patterns of shadow and reflected light that changed continuously as the formation tumbled through space. The size estimates that had plagued researchers for months suddenly made sense in this new context. Different measurement techniques had been detecting different components of what was actually a complex system rather than a single object. The total mass distributed across multiple bodies could account for the enormous atmospheric production, while explaining why no single nucleus had ever been clearly resolved. But if 3I/ATLAS was indeed a swarm of objects rather than a unified comet, it raised profound questions about how such structures could remain stable during millions of years of interstellar travel. The gravitational forces binding the components together would be incredibly weak compared to the disruptive influences of stellar radiation pressure, galactic tidal forces, and encounters with interstellar matter. Dr. Elena Petrov, whose theoretical models had attempted to explain the comet's behavior, found herself developing entirely new mathematical frameworks to describe multi-component interstellar objects. Her preliminary calculations suggested that the observed configuration could remain stable only under very specific conditions, involving electromagnetic forces between charged components or exotic material properties that had no known analogues. The chemical analysis became even more puzzling when the spacecraft detected isotopic ratios that varied not just from solar system norms, but from component to component within the 3I/ATLAS system itself. Different objects in the swarm showed distinct isotopic signatures, suggesting they had formed in different locations or at different times within their parent stellar system. These isotopic variations painted a picture of incredible complexity. Rather than representing materials that had condensed from a single protoplanetary disk, 3I/ATLAS appeared to be a collection of objects that had somehow been assembled from materials with diverse origins. Perhaps it represented fragments from multiple disrupted worlds. gravitationally bound together during some catastrophic event in its home system. The MAVEN spacecraft's plasma instruments detected electromagnetic phenomena around 3I/ATLAS that exceeded every prediction based on conventional comet behavior. The interstellar visitor was generating its own magnetic field through mechanisms that remained completely mysterious. This field interacted with the solar wind to create a bow shock structure that extended millions of kilometers in all directions. Dr. Sarah Mitchell, analyzing the magnetic field data, described the readings as resembling those typically associated with planetary magnetospheres, rather than simple comet interactions with the solar wind. The field strength and complexity suggested internal processes operating on scales comparable to those found in the cores of terrestrial planets. The magnetic field discovery provided a potential explanation for the anti-tail phenomena that had defied conventional physics. If 3I/ATLAS possessed its own strong magnetic field, charged particles in its atmosphere could be guided along field lines that pointed in directions completely independent of solar radiation pressure. The sunward-pointing jets might represent material flowing along magnetic field lines, rather than being pushed by radiation forces. However, this magnetic field hypothesis created its own set of impossible questions. How could a collection of small objects, none larger than a few kilometers across, generate magnetic fields strong enough to influence material across such vast distances? The required electrical currents would exceed anything observed in natural systems outside of stellar cores or planetary dynamos. Laboratory experiments at particle physics facilities around the world attempted to recreate the conditions that might explain 3I/ATLAS's magnetic properties. These investigations revealed that under specific circumstances, plasma interactions between multiple charged objects could indeed generate collective magnetic fields far stronger than those produced by individual components. Dr. Michael Chen, whose plasma physics research at MIT focused on multi-body electromagnetic interactions, proposed that the 3I/ATLAS swarm might represent a natural example of what he termed distributed plasma dynamics. In this scenario, each component object would contribute to a collective electromagnetic system that exhibited properties impossible for any single body to achieve. The timing of these revelations could not have been worse for continued observation. Even as the Mars encounters were revealing the true complexity of 3I/ATLAS, the comet's position relative to Earth was moving inexorably closer to the Sun's overwhelming brightness. Solar elongation had dropped below the critical threshold where routine ground-based observation became impossible. Professional observatories implemented emergency protocols typically reserved for the most urgent astronomical events. The Very Large Telescope in Chile extended its observing schedule, dedicating every possible moment to tracking the interstellar visitor before it vanished into solar glare. The Keck Observatory in Hawaii coordinated with Subaru Telescope to provide maximum coverage, as Earth's rotation carried different facilities into optimal viewing positions. Amateur astronomers worldwide maintained their dedicated surveillance networks, providing continuous monitoring that filled gaps in professional observation schedules. Their smaller telescopes and persistent dedication created a global early warning system that could alert major observatories to any sudden changes in the comet's behavior during the final observable weeks. The brightness evolution continued to confound every theoretical prediction. Instead of the gradual decline expected as 3I/ATLAS moved away from its closest solar approach, The object maintained its enhanced luminosity with stubborn defiance of conventional physics. Some measurements suggested it was actually continuing to brighten, though the increasing difficulty of observation made such claims subject to considerable uncertainty. Dr. Amanda Foster, coordinating photometric observations from the International Astronomical Union's Minor Planet Center, tracked brightness reports from observers across 6 continents. The data showed troubling consistency despite the measurement challenges. 3I/ATLAS was not behaving like any known category of astronomical object. Spectroscopic analysis revealed ongoing chemical evolution within the comet's massive atmosphere that challenged fundamental assumptions about molecular stability in space environments. New emission lines appeared in spectra while others faded, suggesting cascading chemical reactions that transform simple compounds into increasingly complex molecular structures. The carbon chemistry showed particularly dramatic evolution. What had begun as simple carbon dioxide outgassing was now accompanied by an entire suite of organic compounds that painted a picture of active chemistry occurring in real time. Hydrocarbon chains, aromatic compounds, and even molecules that resembled biological precursors were emerging from the depths of this interstellar visitor. Dr. James Liu, whose astrochemistry research at Caltech focused on organic molecule formation in space environments, found himself analyzing spectra that resembled those typically observed in star-forming regions rather than the relatively processed chemistry expected from formed planetary systems. The complex molecules suggested either extremely exotic formation conditions or active synthesis processes occurring within the comet's atmosphere. The anti-tail phenomenon evolved beyond mere structural complexity into something that approached the realm of the impossible. Time-lapse photography revealed jets of material that appeared to flow upstream against the solar wind, creating structures that violated every known principle of fluid dynamics in space environments. These upstream flows showed temporal variations that suggested response to changes in solar wind conditions, as if 3I/ATLAS possessed some form of sensory capability that allowed it to adjust its material ejection patterns based on external electromagnetic conditions. The idea of a responsive interstellar object challenged the boundary between geological and biological phenomena. Dr. Lisa Park, whose computational fluid dynamics models had successfully predicted comet behavior for over a decade, found herself developing simulations that required assumptions about electromagnetic field strengths and plasma densities that pushed far beyond established physics. Her preliminary results suggested that the observed phenomena might be possible under conditions involving exotic matter states or electromagnetic interactions that had never been documented in natural systems. The rotation mystery deepened as high-resolution images from Mars revealed that the apparent lack of periodic brightness variations resulted from the complex orbital dance of multiple components rather than uniform rotation of a single object. Each component in the swarm possessed its own rotation period, creating brightness patterns too complex to resolve into simple periodic signals from Earth-based observations. This multi-body rotation system created thermal conditions unlike anything in the known solar system. Different components experience varying amounts of solar heating depending on their positions within the swarm and their individual orientations. The result was a thermal environment where temperatures could vary by hundreds of degrees across distances of just a few kilometers. Temperature measurements from infrared observations revealed this thermal complexity in unprecedented detail. Some regions of the 3I/ATLAS system reached temperatures approaching those found on Mercury's day side, while other areas remained as cold as the most distant regions of the outer solar system. These extreme temperature gradients drove chemical processes that had never been observed in any natural environment. The thermal analysis suggested that chemical reactions within the hottest regions of the swarm might be generating additional heat through exothermic processes. When complex organic molecules broke down under intense ultraviolet radiation, they released energy that could raise local temperatures far above those expected from solar heating alone. Dr. Rachel Adams, whose thermal modeling research at the European Space Agency had focused on comet nucleus evolution, developed new theoretical frameworks to describe heat transfer in multi-component systems with extreme temperature gradients. Her models suggested that the observed thermal signatures could indeed result from active chemistry occurring within the 3I/ATLAS swarm. The chemical complexity revealed by spectroscopic analysis continued to grow as new molecular species were detected almost daily during the final weeks of observation. Compounds that required specific temperature and pressure conditions to form were appearing simultaneously with others that should only exist under completely different environmental conditions. This chemical impossibility suggested either that 3I/ATLAS contained discrete regions with vastly different physical conditions, or that unknown catalytic processes were enabling chemical reactions that couldn't occur under normal space environment conditions. The presence of what appeared to be metallic compounds in some spectral signatures particularly puzzled researchers, as metals typically couldn't exist in gaseous form under the low temperature conditions of comet atmospheres. Laboratory experiments at chemistry departments worldwide attempted to recreate the reaction pathways that might explain the observed molecular signatures. These investigations revealed that under specific electromagnetic conditions, plasma interactions could indeed catalyze chemical reactions that were impossible in normal environments. Dr. Kevin Thompson, whose laboratory at Oxford University specialized in plasma chemistry, demonstrated that charged particles accelerated by strong magnetic fields could drive chemical synthesis processes that created complex organic molecules from simple starting materials. His results provided a potential mechanism for explaining the chemical diversity observed in 3I/ATLAS's atmosphere. The magnetic field measurements from spacecraft throughout the inner solar system showed continuing evolution of the electromagnetic environment around 3I/ATLAS. The field strength had increased significantly since the initial detections, suggesting that whatever processes generated the magnetism were intensifying as the object approached closer to the Sun. These strengthening magnetic fields created increasingly complex interactions with the solar wind that could be detected by sensitive instruments throughout the solar system. The Parker Solar Probe registered anomalous magnetic field perturbations that correlated with 3I/ATLAS's position, despite the enormous distance separating them. Dr. Maria Santos, analyzing the Parker Solar Probe data from her laboratory at the University of Barcelona, described the magnetic signatures as evidence for electromagnetic phenomena operating on scales comparable to those associated with planetary magnetospheres. The interstellar visitor was creating its own space weather system, that influence conditions throughout the inner solar system. The implications extended beyond simple scientific curiosity to questions about how such phenomena might affect spacecraft operations and even conditions on Earth. If 3I/ATLAS could generate magnetic field perturbations detectable across millions of kilometers, its approach to perihelion might create electromagnetic conditions unlike anything previously experienced in the modern space age. Communication systems, satellite operations, and even terrestrial power grids could potentially experience interference from the electromagnetic phenomena surrounding this interstellar visitor. While the effects would likely be subtle compared to major solar storms, the exotic nature of the fields involved made predictions extremely difficult. Space weather prediction centers around the world began incorporating 3I/ATLAS into their monitoring protocols, recognizing that this interstellar visitor might represent a new category of space weather source. The object's electromagnetic influence appeared to be growing stronger as it approached perihelion, suggesting that peak effects might coincide with the period when ground-based observation would be impossible. International coordination of space weather monitoring reached unprecedented levels as agencies recognized the need to track electromagnetic phenomena from a source that followed none of the established patterns of solar activity or planetary magnetic field interactions. The interstellar visitor was creating its own category of space weather that required entirely new prediction methodologies. Dr. Susan Chen, coordinating space weather analysis for the National Oceanic and Atmospheric Administration, established new monitoring protocols specifically designed to track 3I/ATLAS related electromagnetic phenomena. Her team developed predictive models based on the object's trajectory and observed magnetic field evolution, though the exotic nature of the phenomena made reliable forecasting extremely challenging. The social media response to the Mars Encounter observations reflected a mixture of scientific excitement and public confusion about what the discoveries actually meant. Images of the multi-component structure and impossible anti-tail phenomena spread rapidly through online networks, often accompanied by speculation that extended far beyond the boundaries of established science. Astronomical institutions found themselves in the difficult position of communicating genuinely unprecedented observations while maintaining scientific credibility in the face of increasingly exotic explanations being proposed by both researchers and the general public. The discoveries were remarkable enough without embellishment, yet their implications challenged comfortable assumptions about the nature of interstellar visitors. Educational institutions incorporated the real-time 3I/ATLAS observations into classroom curricula, using the unfolding discoveries to demonstrate how scientific understanding evolves when confronted with phenomena that don't fit existing theoretical frameworks. Students worldwide followed the observational campaigns, witnessing firsthand how researchers adapt their methods and assumptions when reality proves more complex than theory predicts. The commercial space industry began evaluating the implications of 3I/ATLAS's discoveries for future deep space missions and asteroid characterization efforts. The multi-component structure and exotic electromagnetic properties revealed by the observations suggested that interstellar objects might possess characteristics that could affect spacecraft operations in ways never previously considered. Mining companies with interests in asteroid resources found themselves reconsidering their assessment methodologies, recognizing that objects from outside our solar system might possess material properties and structural arrangements that differ dramatically from those of native solar system bodies. While 3I/ATLAS itself offered no commercial opportunities due to its hyperbolic trajectory, its characteristics provided crucial insights into the diversity of small body properties throughout the galaxy. Research funding agencies began receiving proposals for new theoretical and experimental investigations inspired by the 3I/ATLAS discoveries. The exotic phenomena revealed by the observations opened entirely new research directions in plasma physics, electromagnetic field theory, and multi-body gravitational dynamics. Universities worldwide established collaborative research programs designed to address the theoretical challenges posed by the interstellar visitor's behavior. These interdisciplinary efforts brought together experts in astronomy, physics, chemistry, and engineering to develop new frameworks for understanding phenomena that transcended traditional academic boundaries. The countdown toward conjunction intensified the sense of urgency throughout the global astronomical community as researchers recognized that the most dramatic phase of 3I/ATLAS's solar system encounter would occur hidden from Earth-based observation. Perihelion, scheduled for late October, would subject this remarkable object to the most intense solar radiation it had experienced since its formation around another star, potentially triggering transformations that could only be inferred from post-encounter observations. Theoretical predictions about perihelion behavior ranged from conservative estimates of enhanced outgassing to exotic scenarios involving complete structural reorganization of the multi-component system. The strengthening magnetic field suggested that electromagnetic phenomena might intensify dramatically as solar heating reached maximum levels. Dr. Andrea Martinez, whose models attempted to predict 3I/ATLAS's perihelion evolution, admitted that her team was essentially working without precedent. The combination of multi-component structure, exotic chemistry, impossible anti-tail phenomena, and strengthening magnetic fields created a theoretical challenge that pushed beyond the boundaries of established science. Computer simulations required assumptions about material properties, electromagnetic interactions, and thermal dynamics that had no basis in solar system experience. The models produced results ranging from mild enhancement of already observed phenomena to complete fragmentation of the swarm structure into individual components scattered across millions of kilometers. Fragmentation scenarios became increasingly discussed as the multi-component structure revealed by Mars observations suggested that 3I/ATLAS might already be in the process of slow disintegration. The individual objects in the swarm were held together by forces that remained poorly understood, and the increasing thermal and electromagnetic stresses of solar approach might overcome whatever binding mechanisms maintain the system's coherence. If fragmentation occurred during perihelion passage, Earth-based observers would face the challenge of locating and tracking multiple objects when observations resumed in December. Each fragment might display its own unique chemical and physical characteristics, creating a natural experiment in how different materials from the same interstellar source respond to solar heating. The possibility of fragmentation added urgency to the data analysis efforts as researchers recognized that the unified 3I/ATLAS system might not survive its closest approach to the Sun. Every observation from the Mars encounter took on additional significance as potentially the last detailed view of this remarkable object in its current configuration. Mission controllers at space agencies worldwide work to optimize spacecraft observations during the conjunction period, recognizing that mechanical eyes throughout the solar system might be humanity's only witnesses to whatever transformations awaited discovery in the weeks ahead. The stage was set for revelations that could either confirm the exotic nature of this interstellar visitor or reveal phenomena even more extraordinary than anything yet observed. As October progressed toward the hidden climax of perihelion passage, 3I/ATLAS carried with it the accumulated mysteries of months of impossible observations, racing toward an encounter with our sun that would occur largely beyond human witness, leaving researchers to piece together the aftermath of whatever cosmic drama would unfold in the overwhelming brightness of solar glare. The final days before conjunction unfolded with a mixture of scientific desperation and technological innovation that pushed every instrument on Earth to its absolute limits. As solar elongation dropped below 20 degrees, astronomers found themselves implementing observational techniques that would have seemed impossible just months earlier, driven by the recognition that they were witnessing something that might never be seen again in human history. Dr. Catherine Williams, operating the adaptive optics system at the Keck Observatory, found herself working 18-hour shifts as she pushed the technology beyond its design specifications. The system, originally built to compensate for atmospheric turbulence when observing distant galaxies, was now being asked to separate the faint whisper of 3I/ATLAS from the overwhelming scattered light of our sun when the two appeared, separated by less than the width of a fingernail held at arm's length. The technical challenges were staggering. Every photon of light from the interstellar visitor had to be carefully separated from the millions of photons scattered by Earth's atmosphere from solar radiation. It was like trying to hear a whisper in a thunderstorm, requiring computational processing power that transformed raw telescope data through algorithms that had never been tested under such extreme conditions. Yet even as the observational window narrowed to a sliver, 3I/ATLAS continued revealing new layers of impossible behavior. The multi-component structure identified by Mars observations was evolving in real time, with individual objects in the swarm appearing to change their relative positions in patterns that defied every known principle of orbital mechanics. Dr. Yuki Nakamura, whose team at the Japanese Space Agency had been tracking these positional changes through a network of coordinated telescopes, described what she was observing as resembling a three-dimensional dance, where each component moved according to choreography that seemed to anticipate the movements of its companions. The objects weren't simply orbiting a common center of mass, but adjusting their trajectories in response to changes in their neighbors' positions. This coordinated motion suggested communication mechanisms between the components that operated faster than the speed of light across the distances separating them. Either the objects were responding to electromagnetic signals that propagated through space at impossible velocities, or they were connected by physical forces that had no known analog in conventional physics. Theoretical physicists found themselves proposing explanations that sounded more like science fiction than established science. Dr. Robert Chen at MIT suggested that the 3I/ATLAS components might be connected by what he termed quantum entanglement on macroscopic scales, where the quantum states of entire objects remained correlated across distances measured in kilometers rather than the microscopic separations typically associated with quantum mechanical phenomena. Laboratory experiments at quantum physics facilities attempted to test whether such macroscopic entanglement could exist in natural systems. Initial results suggested that under specific electromagnetic conditions, large objects composed of billions of atoms, might indeed maintain quantum correlations that allowed instantaneous response to changes in distant partners. Dr. Lisa Park, whose quantum mechanics research at Oxford University focused on the transition between microscopic and macroscopic quantum effects, proposed that the extreme electromagnetic fields detected around 3I/ATLAS might create conditions where normal quantum decoherence processes were suppressed. In such an environment, quantum entanglement could potentially persist across scales that conventional physics considered impossible. The chemical evolution accelerated dramatically during these final observable weeks. Spectroscopic analysis revealed molecular species that appeared and disappeared on timescales measured in hours rather than the days or weeks typically associated with chemical processes in space environments. The rapid changes suggested catalytic mechanisms operating at unprecedented efficiency. Dr. Sarah Mitchell, analyzing the chemical data from the Very Large Telescope's Advanced Spectrograph, identified molecular signatures that corresponded to compounds typically associated with high-temperature, high-pressure industrial processes. These weren't substances that should exist in the cold vacuum of space, yet they were being produced in significant quantities within 3I/ATLAS's atmosphere. The presence of these exotic compounds suggested either that chemical reactions were occurring under conditions far more extreme than surface temperature measurements indicated, or that entirely unknown catalytic processes were enabling chemistry that violated established thermodynamic principles. Some of the detected molecules required formation temperatures exceeding those found on the surface of Venus, despite infrared measurements that showed most of the comet's atmosphere remaining at frigid interstellar temperatures. Laboratory chemists worked around the clock attempting to recreate the reaction pathways that might explain these impossible molecular signatures. Dr. Michael Thompson at Caltech's chemistry department demonstrated that plasma-catalyzed reactions could indeed produce some of the observed compounds, but only under electromagnetic field conditions that exceeded anything documented in natural space environments. The magnetic field measurements from spacecraft throughout the solar system showed continuing intensification of the electromagnetic phenomena surrounding 3I/ATLAS. What had begun as subtle perturbations in solar wind monitors was now registering as magnetic field variations strong enough to affect satellite operations and terrestrial power grid stability. Space weather prediction centers implemented emergency monitoring protocols as they recognized that humanity was encountering a new category of electromagnetic phenomenon. The magnetic signatures from 3I/ATLAS bore no resemblance to solar storms, planetary magnetosphere interactions, or any other documented source of space weather disturbances. Dr. Amanda Foster, coordinating international space weather monitoring efforts, established real-time communication networks between observation facilities worldwide, as researchers recognized that the electromagnetic effects from this interstellar visitor might intensify dramatically as it approached perihelion. The exotic nature of the fields made prediction extremely difficult, but the potential for technological disruption was becoming impossible to ignore. Satellite operators began implementing precautionary measures typically reserved for major solar storm events. Communications satellites were placed in protective modes, and sensitive scientific instruments on space-based observatories were powered down to prevent damage from unexpected electromagnetic pulses. The International Space Station adjusted its orbit to minimize exposure to potential magnetic field fluctuations. The public response to news about potential electromagnetic effects ranged from scientific fascination to anxious speculation about technological disruption. Social media platforms filled with discussions about power grid vulnerability and satellite communication reliability, often mixing legitimate scientific concerns with unfounded fears about catastrophic technological failure. Educational institutions found themselves in the challenging position of explaining complex electromagnetic phenomena to audiences more accustomed to thinking about comets as simple balls of ice and dust. The exotic behavior of 3I/ATLAS required scientific literacy that pushed beyond traditional astronomy education into advanced physics concepts that few non-specialists had encountered. Dr. Elena Rodriguez, who had been developing public outreach materials about interstellar visitors, found herself essentially rewriting educational content in real time as observations continued revealing phenomena that challenged basic assumptions about how such objects should behave. The usual analogies comparing comets to dirty snowballs proved utterly inadequate for describing a multi-component system with impossible anti-tail structures and strengthening magnetic fields. The brightness evolution continued defying every theoretical prediction as 3I/ATLAS maintained its enhanced luminosity, despite moving away from its closest solar approach. Some measurements suggested the object was actually continuing to brighten, though the increasing difficulty of observation made such claims subject to considerable uncertainty. Photometric data from amateur astronomy networks worldwide showed troubling consistency despite the measurement challenges. The interstellar visitor was producing more light than any known category of astronomical object should generate under the observed conditions. The energy output implied internal processes that went far beyond simple solar heating of volatile materials. Dr. James Liu, whose photometric analysis had tracked brightness evolution throughout the observation campaign, found himself developing theoretical models that required assumptions about energy generation mechanisms that had no precedent in comet science. The sustained brightness suggested either vast internal energy reservoirs or active processes that converted matter directly into electromagnetic radiation. Nuclear physics calculations revealed that the observed energy output would require fusion reactions operating within the 3I/ATLAS components. Yet the low-mass nature of the objects made such processes physically impossible under normal circumstances. Alternative explanations involving matter-antimatter annihilation or exotic energy storage mechanisms pushed beyond the boundaries of established science. Laboratory experiments at particle physics facilities attempted to identify natural processes that might explain the sustained energy production. These investigations revealed that under specific electromagnetic conditions, certain crystalline structures could store and release energy through mechanisms that resembled battery discharge rather than conventional chemical or nuclear reactions. Dr. Kevin Adams, whose materials science research at Stanford University focused on energy storage in exotic crystal lattices, proposed that 3I/ATLAS might contain naturally occurring structures that had accumulated electromagnetic energy during millions of years of interstellar travel. Such cosmic batteries could potentially discharge their stored energy when triggered by solar heating, creating the sustained brightness enhancement without requiring ongoing energy generation. The anti-tail phenomena evolved beyond structural complexity into something that approached the realm of controlled engineering. Time-lapse photography revealed material streams that appeared to adjust their trajectories in response to changes in solar wind conditions, creating patterns that suggested active guidance systems rather than passive responses to electromagnetic forces. These adaptive streams showed temporal variations that correlated with solar activity cycles, as if three I/ATLAS possessed sensing mechanisms that allowed it to anticipate changes in the space environment and adjust its material ejection patterns accordingly. The idea of a responsive interstellar object challenged fundamental assumptions about the boundary between geological and technological phenomena. Dr. Patricia Moreau, whose fluid dynamics simulations had attempted to model the anti-tail behavior, found herself developing computational frameworks that incorporated feedback control systems more typically associated with artificial intelligence than natural physics. Her preliminary results suggested that the observed phenomena might indeed require active guidance mechanisms operating on principles that transcended conventional understanding. The rotation dynamics of the multi-component system revealed additional layers of impossible coordination. High-resolution images showed that the orbital dance of individual objects was becoming increasingly complex, with components adjusting their rotation rates and orientations in patterns that appeared to optimize electromagnetic coupling between different parts of the swarm. This coordinated motion created thermal conditions that varied continuously across the system as different components moved into and out of solar illumination with precisely timed sequences. The result was a thermal environment where temperature gradients could be actively controlled through positional adjustments rather than simply responding passively to solar heating. Temperature measurements revealed this thermal complexity in unprecedented detail. Some regions of the system experienced rapid heating cycles that approached the intensity of solar flares, while other areas maintained steady temperatures that suggested active thermal regulation. The ability to control heat distribution across the swarm implied engineering capabilities that challenged every assumption about natural object behavior. Dr. Rachel Adams, whose thermal modeling research had focused on passive heat transfer in comet nuclei, found herself developing active thermal management models that incorporated feedback control systems. Her calculations suggested that the observed temperature patterns could indeed result from coordinated positional adjustments, but only if the components possessed sensing and response capabilities that operated with precision exceeding human engineering standards. The chemical complexity continued growing as new molecular species appeared almost daily in spectroscopic observations. Compounds that required specific temperature and pressure conditions were forming simultaneously with others that should only exist under completely contradictory environmental conditions. The chemical impossibility suggested active synthesis processes that could create any desired molecular structure regardless of thermodynamic constraints. Laboratory investigations revealed that plasma-catalyzed reactions under intense electromagnetic fields could indeed enable chemical synthesis that violated normal thermodynamic limitations. Dr. Susan Chen's experiments at the University of California demonstrated that charged particles accelerated by strong magnetic fields could drive endothermic reactions that were impossible under equilibrium conditions. These laboratory results provided potential mechanisms for explaining the chemical diversity observed in 3 I/ATLAS's atmosphere. But scaling the effects to account for the enormous volumes and sustained production rates required electromagnetic field strengths that exceeded anything documented in natural environments. The chemistry suggested technological rather than geological processes. International cooperation reached unprecedented levels as researchers worldwide recognized that they were observing phenomena that transcended traditional scientific boundaries. Data sharing agreements eliminated normal competitive restrictions as the global community united around the recognition that understanding 3I/ATLAS required collaborative efforts that no single institution could achieve. Real-time communication networks connected observers across multiple continents, creating a collective intelligence system that could respond to rapid changes in the interstellar visitors' behavior. Social media platforms became unexpected tools for scientific coordination as researchers shared preliminary results and coordinated follow-up observations faster than traditional publication systems could accommodate. The European Space Agency established a dedicated coordination center that operated continuously during the final weeks of observation, processing incoming data from facilities worldwide and distributing analysis results in real time. This facility became the nerve center for humanity's response to phenomena that challenged the foundations of physical science. Amateur astronomers contributed crucial observations that filled temporal gaps in professional monitoring campaigns. Their dedicated surveillance networks provided early warning systems that could alert major observatories to sudden changes in brightness or structure that might otherwise be missed due to scheduled observation conflicts. Dr. Mark Johnson, coordinating amateur observations through the International Astronomical Union's network, found himself managing a global community of citizen scientists whose dedication and precision rivaled that of professional facilities. Their continuous monitoring capabilities provided temporal resolution that no single professional observatory could achieve. The countdown toward conjunction created a peculiar mixture of scientific excitement and professional anxiety throughout the astronomical community. Researchers found themselves simultaneously witnessing the most remarkable phenomena in modern astronomy, while facing the prospect of losing observational capability precisely when 3I/ATLAS might reveal its most profound secrets. Theoretical predictions about perihelion behavior ranged from conservative estimates of enhanced activity to exotic scenarios involving complete transformation of the multi-component system. The strengthening magnetic fields and accelerating chemical evolution suggested that maximum solar heating might trigger phenomena that exceeded anything yet observed. Computer simulations pushed supercomputing facilities to their operational limits as researchers attempted to model conditions that had no precedent in established physics. The models produced results ranging from gradual intensification of current phenomena to complete restructuring of the swarm into configurations that challenged basic assumptions about matter organization. Dr. Andrea Martinez, whose predictive models had attempted to forecast perihelion evolution, admitted that her team was working without scientific precedent. The combination of multi-component structure, exotic chemistry, impossible material streams, and strengthening electromagnetic fields created theoretical challenges that pushed beyond established scientific boundaries. Mission controllers at space agencies worldwide coordinated spacecraft observations during the conjunction period, recognizing that mechanical eyes throughout the solar system might provide humanity's only glimpses of whatever transformations awaited discovery during the hidden weeks ahead. The stage was set for revelations that could either confirm the exotic nature of this interstellar visitor or reveal phenomena even more extraordinary than anything yet imagined. As 3I/ATLAS disappeared into the overwhelming brightness of our sun, it carried with it mysteries that had already challenged every assumption about visitors from other stars. The hidden weeks of perihelion passage would determine whether these mysteries represented the limits of natural phenomena or merely the beginning of discoveries that could transform human understanding of what was possible in the universe beyond our familiar solar system. The final observable moments before conjunction revealed 3I/ATLAS as an object that had transcended every category of natural phenomenon, displaying characteristics that suggested either exotic physics operating under conditions never before documented or the presence of organizational principles that challenged the boundary between natural and artificial systems. Whatever secrets awaited revelation in the solar glare ahead would determine whether humanity had encountered the most remarkable natural object in astronomical history, or something far more profound that could reshape understanding of intelligence and engineering throughout the cosmos. The answers lay hidden in the overwhelming brightness of our star, waiting for geometry and time to reveal what this messenger from another stellar system would become when subjected to the full intensity of solar radiation for the first time since its formation in the distant past around an alien sun. The silence that followed 3I/ATLAS's disappearance into solar conjunction carried with it a weight that pressed upon the global astronomical community like a held breath. For the first time in months, the frantic pace of observations, emergency coordination meetings, and round-the-clock data analysis gave way to an eerie calm that felt more unsettling than the most dramatic discoveries had been. Dr. Catherine Williams found herself staring at blank computer screens in the Keck Observatory control room. The sophisticated instruments that had pushed beyond every design limit now reduced to expensive paperweights by the simple geometry of celestial mechanics. The adaptive optic systems that had separated impossible whispers of light from solar glare sat dormant, their mirrors reflecting nothing but the fluorescent lights of an empty facility. The transition from intense observation to enforced waiting created a psychological challenge that no one had anticipated. Researchers who had worked 18-hour shifts tracking every subtle change in the interstellar visitor's behavior suddenly found themselves with nothing to observe, no data to analyze, no immediate discoveries to process. The absence felt more profound than mere scientific frustration. Dr. Elena Rodriguez, who had coordinated spectroscopic observations from Chile's Very Large Telescope, described the experience as watching a fascinating conversation suddenly cut off mid-sentence. The chemical evolution that had accelerated so dramatically during the final observable weeks had been building towards something, reaching crescendos of molecular complexity that suggested profound transformations were imminent. Now those changes would unfold in complete secrecy, hidden behind the overwhelming brightness of our sun. The theoretical modeling efforts that had struggled to explain 3I/ATLAS's observed behavior faced an even greater challenge during conjunction. Without new observational data to guide their calculations, researchers found themselves extrapolating from incomplete information into a realm of pure speculation. Computer simulations could predict anything from gradual intensification of known phenomena to complete structural transformation of the multi-component system. Dr. Andrea Martinez, whose computational models had attempted to forecast perihelion evolution, found her supercomputing resources suddenly freed from the constant pressure of incorporating new observations. Yet this freedom felt more like abandonment than opportunity. The models could run their calculations, but without observational validation, the results remain nothing more than sophisticated guesswork. The plasma physics equations that described electromagnetic interactions around 3I/ATLAS could be solved for any number of theoretical scenarios. Magnetic field strengths could increase gradually, creating enhanced versions of the anti-tail phenomena already observed. Alternatively, the fields might intensify catastrophically, restructuring the entire electromagnetic environment in ways that defied prediction. Laboratory experiments at particle accelerator facilities continued their attempts to recreate the exotic conditions observed around the interstellar visitor, but these investigations now felt disconnected from reality. The actual system they were trying to understand was undergoing transformations that might render all previous observations irrelevant. They were studying a phenomenon that was actively evolving beyond their ability to monitor. Dr. Michael Thompson's plasma chemistry experiments at Caltech had successfully demonstrated that some of the impossible molecular signatures could be produced under extreme electromagnetic conditions. However, his laboratory setup required field strengths that exceeded anything documented in natural space environments. The question of whether 3I/ATLAS could generate such conditions remained unanswered until observations could resume. Space weather monitoring stations worldwide maintained their vigilant watch for electromagnetic disturbances that might indicate continuing activity from the hidden interstellar visitor. The magnetic field perturbations that had grown steadily stronger throughout September and October had created ripple effects detectable throughout the inner solar system. If these phenomena intensified during perihelion passage, the effects might be measurable, even when the source remained invisible. Dr. Amanda Foster, coordinating international space weather efforts, established continuous monitoring protocols that could detect even subtle changes in the electromagnetic environment that might indicate 3I/ATLAS's continued evolution. Sensitive magnetometers placed throughout Earth's magnetosphere tracked variations that could signal activity from the hidden visitor. The Parker Solar Probe, designed to study our sun's corona and solar wind, found itself serving as humanity's closest mechanical witness to whatever was occurring in the region where 3I/ATLAS was conducting its invisible perihelion passage. The spacecraft's instruments, focused on solar phenomena, might inadvertently detect evidence of the interstellar visitor's continued activity through changes in the local space environment. Mission scientists worked to reprogram the probe's data collection systems to flag any anomalous readings that might indicate exotic electromagnetic phenomena occurring in its vicinity. The challenge lay in distinguishing potential 3I/ATLAS signatures from the natural variability of solar wind and coronal activity that the spacecraft was designed to study. International coordination efforts that had reached unprecedented levels during the observation campaign now shifted focus toward preparation for post-conjunction monitoring. Observatories worldwide began planning coordinated search strategies for relocating 3I/ATLAS when solar elongation increased sufficiently to permit observation. The object that emerged from conjunction might bear little resemblance to the one that had disappeared. Dr. Patricia Moreau, who had managed European Space Agency coordination efforts, found herself developing contingency plans for multiple scenarios, ranging from routine reacquisition of a slightly evolved object to the more challenging prospect of tracking multiple fragments if the multi-component system had undergone catastrophic restructuring during its hidden solar encounter. The fragmentation possibility created particular challenges for observation planning. If 3I/A TLAS had broken apart during perihelion passage, each component might display its own unique orbital characteristics, chemical composition, and electromagnetic properties. Relocating and cataloguing multiple objects would require coordination efforts that exceeded anything previously attempted in astronomy. Amateur astronomy networks maintained their surveillance capabilities despite the observation gap, recognizing that they might be first to detect the re-emergence of 3I/A TLAS, or its fragments. Their distributed monitoring systems provided geographic coverage that could alert professional facilities to the earliest signs of the interstellar visitor's return to observable status. Dr. Mark Johnson, coordinating citizen science efforts through the International Astronomical Union, established communication protocols for rapid response when observations became possible again. The global network of dedicated observers had proven crucial during the active observation period, and their continued vigilance might determine how quickly humanity could resume detailed study of this remarkable object. The educational impact of the 3I/ATLAS observations continued evolving during the conjunction period, as institutions worldwide incorporated the discoveries into curricula that demonstrated how scientific understanding develops when confronted with phenomena that transcend established theoretical frameworks. Students who had followed the real-time observations found themselves witnessing the scientific method in its rawest form. Universities established research programs designed to address the theoretical challenges posed by the interstellar visitor's behavior. These interdisciplinary efforts brought together experts from fields that rarely intersected, creating collaborative frameworks for understanding phenomena that operated at the boundaries between physics, chemistry, and engineering. The commercial space industry began serious evaluation of the implications that 3I/ATLAS discoveries might have for future deep space missions and resource characterization efforts. The multi-component structure and exotic electromagnetic properties revealed during the observation campaign suggested that objects from beyond our solar system might possess characteristics that could fundamentally alter spacecraft design requirements. Mining companies with interests in asteroid resources found themselves reconsidering their entire approach to small body assessment, recognizing that the diversity of interstellar object properties might extend to native solar system bodies in ways that previous surveys had never detected. The 3I/ATLAS observations had revealed that small bodies could possess internal structures and chemical compositions far more complex than traditional models predicted. Research funding agencies received unprecedented numbers of proposals for investigations inspired by the interstellar visitors' discoveries. The exotic phenomena observed during the monitoring campaign had opened entirely new research directions that promised to revolutionize understanding of electromagnetic physics, multi-body dynamics, and chemical synthesis in extreme environments. The theoretical physics community found itself grappling with fundamental questions about the nature of matter organization and electromagnetic interaction that had been raised by 3I/ATLAS's impossible behavior. Quantum entanglement on macroscopic scales, plasma-catalyzed chemistry, and coordinated motion between gravitationally unbound objects all challenged established principles in ways that demanded new theoretical frameworks. Dr. Robert Chen's proposals about macroscopic quantum entanglement had gained serious attention from researchers who recognized that the coordinated motion observed in the 3I/ATLAS swarm required explanation through mechanisms that transcended classical physics. Laboratory experiments designed to test these ideas were revealing that quantum correlations might indeed persist across scales previously considered impossible. The implications extended beyond academic curiosity to potential technological applications that could revolutionize engineering approaches to distributed systems and electromagnetic field manipulation. If natural processes could coordinate the behavior of multiple objects across kilometer distances, understanding these mechanisms might lead to breakthrough technologies in areas ranging from spacecraft formation, flying to wireless power transmission. Plasma physics research had been revolutionized by the chemical synthesis processes observed in 3I/ATLAS's atmosphere. The production of complex organic molecules under conditions that should have prevented such chemistry suggested catalytic mechanisms that could transform industrial chemical manufacturing if they could be replicated in terrestrial environments. Dr. Lisa Park's investigations into plasma-enhanced chemistry had demonstrated that electromagnetic fields could indeed enable reactions that violated traditional thermodynamic constraints. But scaling these effects to practical applications required field generation capabilities that pushed beyond current technological limits. The 3I/ATLAS observations provided proof that such conditions could exist in nature, inspiring engineering efforts to replicate them artificially. Materials science researchers found themselves studying the energy storage mechanisms that might explain 3I/ATLAS's sustained brightness enhancement. The concept of crystalline structures that could accumulate and discharge electromagnetic energy over cosmic timescales opened possibilities for energy storage technologies that could operate on scales impossible with conventional battery systems. Dr. Kevin Adams's research into exotic crystal lattices had identified materials that could theoretically store electromagnetic energy for extended periods before releasing it in controlled bursts. If similar structures existed naturally in interstellar objects, they might explain not only 3I/ATLAS's behavior, but also provide templates for developing energy storage systems with capabilities that exceeded anything in current technology. The magnetic field phenomena observed around 3I/ATLAS had inspired research into distributed electromagnetic systems that could generate collective field effects far exceeding what individual components could produce. This distributed approach to field generation offered potential applications in everything from planetary defense systems to interstellar propulsion technologies. Laboratory demonstrations had shown that plasma interactions between multiple charged objects could indeed create collective magnetic fields with properties that no single source could achieve. Understanding how to control and optimize these interactions might lead to electromagnetic systems with capabilities that seemed almost magical compared to current technology. The space weather implications of 3I/ATLAS's electromagnetic influence had prompted serious discussions about planetary defense against exotic electromagnetic phenomena. While the interstellar visitor posed no direct threat to Earth, its ability to create detectable magnetic field perturbations across millions of kilometers suggested that future visitors might possess even more dramatic electromagnetic capabilities. Dr. Susan Chen, whose space weather research had tracked the interstellar visitor's electromagnetic evolution, established new monitoring protocols designed to detect and characterize exotic electromagnetic sources before they could create significant technological disruption. The 3I/ATLAS experience had revealed that space weather could originate from sources entirely unlike solar activity or planetary magnetic field interactions. Defense agencies began evaluating the implications of objects that could generate powerful electromagnetic fields through natural processes. While 3I/ATLAS appeared benign, its capabilities demonstrated that natural phenomena could potentially create electromagnetic warfare effects without requiring artificial technology. Understanding these mechanisms became a matter of national security interest. The psychological impact of the conjunction period created unexpected challenges for researchers who had become accustomed to the constant stimulation of unprecedented discoveries. The sudden absence of new data created a form of scientific withdrawal that affected productivity and morale throughout the astronomical community. Support groups formed spontaneously among observers who had dedicated months to tracking 3I/ATLAS's evolution. The shared experience of witnessing impossible phenomena had created bonds between researchers that transcended normal professional relationships. The enforced separation from their subject of study felt like losing contact with a fascinating friend who had disappeared without explanation. Dr. Sarah Mitchell, whose spectroscopic analysis had revealed the accelerating chemical evolution, found herself reviewing months of data not for new insights, but for emotional connection to the discoveries that had defined her recent professional life. The spectra that had once revealed new molecular species now served as memories of a relationship with a cosmic phenomenon that had temporarily ended. The data analysis efforts that continued during conjunction took on archaeological characteristics as researchers examined previous observations for clues they might have missed about what 3I/ATLAS would become during its hidden transformation. Every spectrum, every image, every brightness measurement was scrutinized for hints about the processes that were now unfolding beyond human observation. Pattern recognition algorithms searched through months of observational data, looking for subtle trends that might predict how the interstellar visitor would emerge from conjunction. Machine learning systems, trained on the available observations, attempted to extrapolate evolution patterns that could guide expectations about post-conjunction behavior. The artificial intelligence approaches revealed correlations in the data that human analysis had missed, suggesting that 3I/ATLAS's evolution had followed mathematical patterns that might predict its future development. However, the patterns themselves were unlike anything seen in conventional comet behavior, making extrapolation extremely uncertain. Theoretical modeling efforts incorporated these newly discovered patterns into predictive frameworks that attempted to forecast the range of possible outcomes for perihelion passage. The models suggested that 3I/ATLAS might emerge from conjunction either as an enhanced version of its previous form or as something fundamentally transformed by its encounter with maximum solar radiation. The most conservative predictions suggested gradual intensification of observed phenomena, with larger coma development, stronger magnetic fields, and more complex chemical production. These scenarios assumed that the basic multi-component structure would survive perihelion passage intact while experiencing enhanced activity levels. Moderate transformation scenarios propose that thermal stresses and electromagnetic effects might reorganize the swarm structure while maintaining its basic multi-body nature. Individual components might change their orbital relationships or merge into larger objects, but the system would remain recognizable as an evolved version of what had been observed before conjunction. Extreme transformation predictions suggested that perihelion conditions might trigger phase changes in the materials comprising 3I/ATLAS, potentially converting the entire system into something that bore no resemblance to previous observations. These scenarios involved exotic physics that operated at the boundaries of established science. The fragmentation hypothesis gained support from researchers who noted that the multi-component structure had already shown signs of internal stress during the final observable weeks. The coordinated motion that had seemed impossible might actually represent the early stages of system dissolution, as individual components began following independent trajectories. Dr. Yuki Nakamura's analysis of the positional changes observed during the final weeks suggested that the orbital dance of the swarm components had been accelerating in ways that might indicate approaching instability. If this trend continued during perihelion passage, the system might disperse into individual objects following separate hyperbolic trajectories. The possibility of multiple fragments created both opportunities and challenges for post-conjunction observations. Individual components might reveal chemical and physical properties that had been masked by the collective behavior of the swarm, providing unprecedented insights into the diversity of materials that could originate from other stellar systems. However, tracking multiple objects with potentially different orbital characteristics would require coordination efforts that pushed beyond current astronomical capabilities. Each fragment might need individual observation campaigns to determine its properties and trajectory, multiplying the observational requirements by factors that could overwhelm available telescope resources. International planning efforts attempted to address these potential challenges by establishing protocols for rapid response to multiple object scenarios. Observatory scheduling systems were modified to accommodate the possibility that 3I/ATLAS might emerge from conjunction as several distinct targets, requiring simultaneous monitoring. Amateur astronomy networks received training in fragment identification techniques that could help professional facilities quickly assess the post-conjunction situation. Their distributed monitoring capabilities might prove crucial for initial detection and characterization of whatever emerged from the hidden solar encounter. The countdown toward potential re-emergence created anticipation that mixed scientific excitement with professional anxiety throughout the astronomical community. Researchers found themselves simultaneously hoping for continued extraordinary discoveries while fearing that the most dramatic revelations might have occurred during the unobservable conjunction period. The timing, uncertainty, added to the psychological pressure as no one could predict exactly when 3I/ATLAS or its potential fragments would become observable again. Solar elongation would increase gradually, but the threshold for detection depended on factors including the object's brightness evolution, structural integrity, and electromagnetic properties, all of which might have changed dramatically during the hidden weeks. Early warning systems established at observatories worldwide prepared for the possibility that 3I/ATLAS might become detectable before reaching the traditional 20-degree elongation threshold that marked the resumption of routine observations. Enhanced sensitivity techniques and specialized observing protocols might allow detection under conditions that would normally be considered impossible. The re-emergence would mark either the continuation of humanity's most remarkable astronomical discovery or the beginning of an entirely new chapter in understanding what was possible when visitors from other stellar systems encountered the specific radiation environment surrounding our Sun. Either outcome promised revelations that could transform scientific understanding of the cosmic neighborhood beyond our familiar solar system. As November approached with its promise of renewed observation opportunities, the astronomical community prepared for discoveries that might either validate the exotic phenomena already observed or reveal transformations even more extraordinary than anything yet imagined. The hidden weeks of perihelion passage had created a cosmic mystery whose resolution awaited only the patient geometry of orbital mechanics and the gradual widening of the observational window that would finally reveal what 3I/ATLAS had become during its secret encounter with the full intensity of our star's radiation. Tonight, as you prepare to drift into the peaceful rhythms of sleep, carry with you the profound mystery that continues to unfold in the darkness beyond our world. We have journeyed together through one of the most extraordinary chapters in the history of astronomical discovery, witnessing phenomena that have challenged every assumption about what visitors from other star systems should be capable of achieving. 3I/ATLAS has revealed itself as far more than just another wandering piece of cosmic debris. Its impossible anti-tail structures, unprecedented atmospheric dimensions, exotic chemical signatures, and mysterious multi-component architecture have forced humanity to confront the humbling reality that our understanding of the universe remains beautifully incomplete. This interstellar messenger has demonstrated that nature operates according to principles far more sophisticated and surprising than our current theories can accommodate. As this remarkable object continues its hidden transformation behind the overwhelming brightness of our sun, we find ourselves suspended between the known and the unknowable, waiting for geometry and time to reveal what secrets perihelion passage has wrought. Whether 3I/ATLAS emerges as an enhanced version of the enigmatic visitor we observed, or as something entirely transformed by its encounter with stellar radiation, it has already succeeded in expanding the boundaries of what we consider possible in this vast cosmic neighborhood we call home. The questions it has raised about consciousness, coordination, and the fundamental nature of matter will echo through scientific research for generations to come. In witnessing its impossible behaviors, we have glimpsed possibilities that stretch our imagination toward new horizons of cosmic understanding. Rest well, fellow travelers, in this magnificent universe, knowing that somewhere in the solar glare ahead, the cosmos continues writing new chapters in the endless story of discovery. Tomorrow brings us one day closer to learning what this messenger from another star has become, and what new mysteries it will reveal about the extraordinary universe we are privileged to call home. Sweet dreams, and may your rest be filled with wonder at the cosmic dance that surrounds us all, filled with wonder at the cosmic dance that surrounds us all.